More recently, then, you started to go into aspects of statistics and sampling and filtering.
Yeah.
What brought you there? And can you sort of give us a general view of the problem?
It started from turbulence because I started to think that maybe what I should do is try to see how people who do irreversible statistical mechanics deal with complicated problems and see if there's something that I could borrow. And I came and therefore started reading up and working with the more expansive formalism of irreversible statistical mechanics, which is very complicated. Also, I became interested in statistics, read up on statistics for some complicated reasons. And the more expansive formalism is presented in ways which are very difficult to read because it's written by physicists and the terminology is hard to, I found it impenetrable. And one thing dawned on me that in fact all it was is a formula for computing conditional expectations. So I had the first version of this idea, of this observation, and I talked about Ule Had, who came up with the correct one, which wasn't the same one I had. And so then it became very interesting to try to see, again, could we do something about turbulence with this formalism, which is actually quite different from what anybody has done. It's very interesting formalism. And then Bob Miller, who was a student here, who I knew, was asking me whether I could make any suggestions about how to do data assimilation, filtering. So it seemed to occur to me that, in fact, there's a connection there that I could. So that got me into data assimilation. Data assimilation got me into sampling, which I'd been interested in before also, but not by this good method. So I developed some sampling algorithms, and so one thing leads to another. And it's certainly the problems of which I'm dealing with now have some of the structural turbulence problems, in the sense that there are large, semi-deterministic, semi-random problems which people cannot do because they're too large.